Bonsoir tout le monde, bienvenue au meeting de Muskie Canada Montréal, the meeting de février 2024. Welcome everybody to the February meeting from the Montreal chapter. Tonight we have a special guest from New Brunswick. His name is Christopher Ryan Hill. He's a researcher at the University of New Brunswick, and he's going to talk to us about two of his research. I don't want to say anything bad, so I'm going to leave it to him to say what he has to say about those researchers. Hi, Christopher. The stage is to you now.
All right.
Whoa, sorry. I'm going to fix that. All right.
So you can see my screen now?
Go ahead, Chris. Your screen is there. You can start the slideshow now.
Okay, so you guys could see that.
Yeah.
Okay, good show. Good deal. All righty. Hi, everybody. Thanks for having me this evening. My name is, I go by Ryan. Call me Christopher if you like. That's my first name, but I'll answer either way. I am a PhD candidate at the University of New Brunswick with the Canadian Rivers Institute. And I'm here this evening to discuss some of my current ongoing research involving muskie and the St. John River. And before I get started, I just wanted to thank our list of partners and sponsors here, because without them, none of this research would be possible. So just a brief overview of my presentation. So I'll start by providing some background information on muskie and the St. John River, as well as an overview of their ecology and its relevance to some of my research. And then I'm going to discuss two specific projects that I'm working on. The first is an investigation of muskie's movement ecology and habitat use relative to environmental conditions that are regulated by hydropower production. And the second project is attempting to design and implement a framework for using image recognition as a tagging method for muskie research and population monitoring. So the St. John River begins with its headwaters in eastern Quebec and Maine, so approximately 30% of the watershed is in its headwaters in those regions, and it flows approximately 700 kilometers through New Brunswick, where it empties into the Bay of Fundy. So the St. John River is heavily regulated by hydropower. So there are numerous dams throughout the watershed, including 3 major dams along the main stem, which has had a dramatic effect on the aquatic ecosystems in the river. So muskie are an established species in the St. John River. They were introduced in Lac Frontière in the 1970s, and since then they have become established throughout the St. John River all the way down to the head of tide. So they're a popular sport fish, ever increasingly. So we've got an impressive fishery developing here. It's pretty good angling. We're enjoying it. So a bit of background on muskie ecology and what makes them interesting subjects for some of my broader research. So muskie the muskie is a highly evolved, specialized fish. They're apex predators. As I'm sure everyone listening knows, they generally use a lie-in-wait strategy or an ambush strategy to feed. But their physiology it's a reflection of natural selection for traits, behaviors, and life history strategies that have allowed them to be successful in natural lakes and rivers. But their physiology, consequently, also makes them particularly sensitive to metabolic stressors. So these include things like excessive exercise, overexertion, as well as rapid changes in environmental conditions. So one of my biggest areas of research seeks to understand how hydropower production impacts fish behavior. So in many cases, hydroelectric dams act as buffers for the electrical grid that they service. And this is because hydroelectric dams can adapt to energy demands more rapidly than other types of energy production, because all they have to do is alter the amount of water that they're letting through turbines. So regulating discharge like this can have dramatic effects on conditions in the surrounding aquatic environment. And if changes occur more rapidly than fish can adjust to them, it may have negative consequences on fitness and survival. So the first study that I'm going to discuss is a fine-scale telemetry study, where I am investigating how muskie behaviors change in response to hydropower production and fluctuating environmental conditions. So this study was conducted in the tail race of the Mactaquac generating station. So Mactaquac is the largest and lowermost hydroelectric dam in the St. John River, and it's the primary regulator of flow conditions in the lower section of the river, so around 115 kilometers lower section of the river. And it turns out that there is a population of muskie that either live in this area or they move in and out of the area transiently, but use the area for a large proportion of the year. And this is the perfect scenario for a field experiment because, number one, this habitat is directly connected to the source of change, being the dam. And B, or number two, because the fish in this habitat stay there long enough that we can observe their behaviors over a wide range of environmental conditions, which this makes it easier for us to understand the relative contributions of different environmental variables, which tend to be correlated together. So it can be difficult to disentangle relative influences. So I'll tell you a bit about fine-scale telemetry. So this is a relatively new technology at the scene that allows us to track fish movements in three-dimensional space. And in principle, this type of telemetry needs two things to work. The first is we need fish that are tagged with special acoustic tags that transmit a signal at specific intervals. So like we use every 7 seconds usually. And each tag transmission includes different types of information that includes a unique identification code for each tag, as well as temperature and pressure readings from the time of transmission. And the second thing that we need is an array or a grid arrangement of hydrophones, which detect and decode the information that's transmitted in the signals from the tags. So the principle is that as long as we know the exact position of each hydrophone in the water, meaning we know their position and the distance between their positions in three-dimensional space, and we know the speed of sound in water, which is just a linear function of the ambient water temperature, we can estimate the position of a tag at the time that it transmits a ping based on the difference in the time of arrival at each hydrophone. So in other words, it's the amount of time it takes for the same transmission to be heard by each hydrophone, which in this case, distance is just a function of speed. And this is what we call triangulation, which I'm illustrating in the bottom right figure. So for our methods in the study that we conducted, we tagged 45 muskie in the Mactaquac tail race, so within that area shown on that map on the previous slide. So these tags were implanted surgically in the abdominal cavity of each fish. So you can see that in the top right photograph there, where I've made an incision in the fish's belly and inserted the tag and stitched it back up. So these tags had ping rates of 7 seconds, like I said, and they're relatively high output tags at 76 kilohertz. So they only last 150 days. But so in theory, as long as fish are within that hydrophone or within that area that's covered by the hydrophone array, we should have a position of the fish every 7 seconds along with a body temperature reading, as long as it stays in that area. So all the things I'm showing here is sort of interesting. How do we, you may be wondering how we actually deploy these things below a 670 megawatt hydroelectric dam. There's a lot of flow going on there. And these things obviously have to remain still for the technology to work. So we deployed these hydrophones on these custom designed 600-pound steel anchors that were designed to minimize hydraulic drag so they don't move in the flow. And then so we put these down on the substrate using a winch attached to this large barge. We collected the coordinates of the locations using differential GPS. So our deployment period, these went out and fish were tagged in July of 2023, and it all stayed in until December, around mid-December. And then to get the hydrophones back out, we have divers. It's a similar process. We just have to have divers go down and attach our winch line to the anchors to pull them back up. And from them, we can download the data. So the telemetry data from this study is still being processed. So when we actually pull these things out of the water and download the data, all it really gives you is a bunch of numbers and gibberish that's relevant to each hydrophone. So if you recall what I said about triangulation in the previous slide, so the way it works, the position estimate is based on the time that each hydrophone receives the same transmission. And you'll notice that what we need in order for that to work is for each independent hydrophone to be operating on the same clock. And just like any clock in your computers or laptops or phones or any clock, they tend to drift away from a constant time at random rates and in random directions. So before we can estimate positions of fish, we have to synchronize those clocks and quantify error and accuracy through time. So all that is to say that there's several months of processing and computing and modeling involved before we have anything that resembles position estimates. But this animation that I'm showing on the right gives you an idea of what the output is going to look like. So this is from a trial run that I did back in 2021, where I had a small array of hydrophones and I had a few tagged striped bass in the area. So each of those little dots that you see are striped bass, individual striped bass swimming around. And those are their exact positions within 5 meters accuracy. So at this point, from the muskie data from this year, what I can say is that we have an incredible amount of data from the muskie, much more than I collected from this striped bass test set. So the raw data coming out of the hydrophones had around 80 million detections, which was something like 50 gigabytes worth of raw text. And so when this is all said and done, this is certainly going to be one of, if not the most detailed data set of muskie behavior that currently exists, particularly in a natural setting in the wild. And so one thing I haven't mentioned yet is what we're going to do with this data once we have it. So once the telemetry data is processed and we have the three-dimensional positions of the fish throughout that time, what we're planning to do is combine the three-dimensional telemetry data with three-dimensional hydraulic models. So those will describe the flow conditions that fish experience based on discharge conditions that are coming directly out of the dam. And by considering the hydraulic fields that fish are using, along with other environmental covariates and intrinsic factors, including water temperature and fish activity, these types of things, the result will be high-resolution insight into how fish use and exploit this habitat and how they adjust to changes in environmental conditions in order to minimize energy loss. So that's actually it for the first study that I'm going to discuss. Like I said, it's still in progress. And I'm happy to come back at a later time with you guys and provide a more comprehensive update on the conclusive results of that study once we get to that point. So the second project that I'm going to discuss this evening is developing a framework to use image recognition as a tagging method for muskie research and population monitoring. So traditional mark recapture techniques that we have used forever in fish research and fish biology and management is generally high effort. It's quite time consuming. It involves a lot of effort, and it also requires a fair degree of funding and resources in order to conduct this type of study. And unfortunately, or the unfortunate reality, I guess I should say, is that research and monitoring efforts, they tend to be biased towards species of political or economic significance. And this is largely due to the constraints of funding and the distribution of resources and expertise. And I would personally propose that this type of bias is a major limitation to the progress of modern ecology. So recent studies have shown that advancements in data processing techniques and machine learning techniques may now allow us to identify individual fish or individual animals based on unique skin patterns that we can extract from images. In other words, a simple photograph may be able to serve as an effective tag. And the ability to identify individual fish opens an endless window of opportunity to learn about the fundamental ecology and conservation of species that might not be prioritized by governing agencies and funding resources. And unfortunately, I think the muskie is one species that tends to fall into this category. So potential applications of using image recognition include monitoring population size, monitoring trends in recruitment and expansion, seasonal movement behaviors, habitat selection and quality, and even age growth and trophic ecology. So imagery data like I'm talking about could be extracted from angler surveys and other types of citizen science. It could be pulled from logging applications and web scraping, underwater video surveys. there's a number of ways that we could collect this type of data with minimal effort. And as long as we can collect and process and store that data strategically, it could have serious benefits for our understanding of fish ecology on a wide range of spatial and temporal scales. So in order for this technique to work, there are several conditions that must be true. So first of all, individual fish must have we'll call a biological fingerprint, meaning individuals must have specific skin patterns or morphological features that we can use to distinguish them from other individuals within the population. And additionally, that fingerprint has to remain distinguishable through time as fish experiences growth, injury, changing environmental conditions, and so on. So phenotype and morphology, it is things like pigmentation are plastic, meaning they can be influenced by a number of factors such as environmental conditions that the fish has experienced recently, diet, age, genetics, a number of other factors. So the two big things that we need to establish in order to implement this technique at its full capacity are, first of all, what are the features that, or the morphological features, that we can use to accurately distinguish between individuals? And secondly, what are the controllable factors that maximize our ability to extract and separate those patterns in order to identify individuals? So these are things like image standardization and resolution. These are controllable factors that may contribute to classification accuracy. So to that end, I have been working on a validation study, which is really just a set of tests that are designed to identify the best practices for collecting and processing and storing imagery data that's collected from a variety of sources for use in population monitoring. So the data collection methods that we're using are pretty simple and straightforward. So basically we capture fish, which we do primarily through angling and electrofishing. And when we capture fish, we take a series of standardized and non-standardized photographs on both sides of the fish, as well as the belly of the fish. So we tag those fish with external dart tags, which are just sometimes they're called void tags or spaghetti tags. They have unique ID codes on them so that when you recapture them, you know for sure that it's the same fish. So we tag the fish and we put them back in the water, and hopefully we recapture them at some point again in the future, which we do pretty frequently. I decided to initiate this project because I am either conducting or involved with numerous studies currently in the St. John River, which gives me the opportunity to put my hands simply on a lot of fish. So it's the perfect opportunity to capture individuals at multiple time points throughout their life as they're exposed to natural environmental conditions and understand how consistent different patterns are through time. So lastly, when we recapture the fish, we take the same set of pictures again. So what this gives us is we input it into a database, and here I'm saying we train the machine, which really what we're doing is conducting a series of tests using this really nice database that we're developing. So what it gives us is sets of fish that are known recaptures that have been encountered at different points throughout their life. And a number of other fish that we can compare them to, say fish that we have or have not recaptured it multiple times. And we can compare these different sets of fish under different sets of conditions. So that's meaning we can compare like standardized versus non-standardized images. And we can compare different processing algorithms and approaches to extracting fingerprints and comparing them and see which ones give us because we have known recaptures, we can see which approaches give us the highest classification accuracy. Since we're capturing many of these fish 2, 3, or 4 times at different points in their life, we're hoping to and beginning to understand how consistent different skin patterns are at different locations on the body through time, and as well as different morphological features, and we're able to separate that from the different properties within just the image and data collection techniques that contribute to classification accuracy. So where are we at with our current data set? So currently we have around 200 individuals in our data set. So that's 200 different individuals tagged, and a little over 40 recaptures. So we're using a number of different, at the moment, we're using a number of different image processing softwares and algorithms that currently exist to compare classification performance. And ultimately, our goal with this is to, once we identify those best practices, we want to write a custom open source software that will automate and implement the processing and storage of data using those optimal techniques that we are working on identifying through our series of trials and experimentation. And then we're going to publish that along with a set of guidelines that outline the best practices for data collection or for collecting imagery data. So this also is obviously an ongoing research project. But what we've learned so far is that, number one, yes, muskie can generally be distinguished. An individual muskie can be distinguished from each other based on skin patterns on different parts of their body. And different skin patterns generally remain consistent through time, at least within the time limits that we have seen so far, which we have 2 years of data, which is not that long of time. We found a few things that are obviously reduce classification accuracy and a few things that improve classification accuracy. So things that reduce classification accuracy include different angles. So the top right image there shows what I'm talking about pretty well, but it applies to any, the angler style photographs as well. When the fish body plane is at different angles, different algorithms have trouble dealing with that. But we do have a fix for it. As you can see in that same image, there is possible to straighten the fish out. And that does improve classification accuracy, which is great. Another thing that is troublesome actually is glare. We're working on ways to deal with that, but it's proving to be more challenging than I would have thought, but I think we'll get there. Third thing that clearly affects accuracy is injuries. We can't do anything about injuries, obviously, aside from use different sections of the body. So we consider, so we're pulling fingerprints from different parts of the body and maybe considering other types of morphometric data, such as relative lengths and distances of fins and whatnot, which helps as well, actually. So things that include or that improve classification accuracy include straightening images, as I previously noted, taking burst photographs upon each encounter. So we can feed these different models multiple images from the same encounter, and it considers that all together it has more information to consider about the fingerprint, and that improves classification accuracy. And finally, interestingly enough, it almost seems the opposite of the previous point. It makes sense conceptually, though, is that region restriction, considering smaller spaces within the fish's body, tends to improve classification accuracy. So what's going on is you're pulling fingerprints from a smaller area. So there's less of a chance for things like the angle that the fish is sitting at to contribute to variation in the fingerprint itself. That concludes my presentation. Actually, I'm happy to take any questions at this point. To be perfectly honest, I skimmed through that much faster than I expected myself to.
Hi, Chris. Perfect. It was really interesting from a developer point of view, because I'm a software developer. The last part, I can't wait to get my hands on that open source thing to challenge my hundreds of pictures of muskies.
Yeah.
Here, I have a question for him.
Yeah.
How does he know those 200 that they caught are all different?
I got a question from the crowd here.
Yep.
How do you know that? I think I can answer that, but I will let you answer that. How do you know from the 200 that you caught that 40 something of them are the same fish?
Because every fish that we catch receives an external tag with a different number on it. So when we recapture them, we see that tag, and we can trace back all the previous encounters.
I want to know the first 200 where they don't have another one. How do they know the 200 are all different from photo analysis?
Okay. So how do you know that the first 200 that you caught were different?
Well, so the first 200, so every fish that I'm talking about has a tag. So recaptures only happen.
Okay.
Yeah, so every fish has a tag.
They catch it, they tag it. So if it doesn't have a tag, they didn't have it before. Okay, that answers the questions.
Yeah.
Other questions from the audience?
The question, when do they expect to finish
When did you expect to have that open source framework available?
That's a good question. To be perfectly honest, that the whole image recognition project is something that I have completely bullheaded off the. I've taken on myself, and I'm doing it. It's a side project, I suppose. Okay. So it's I do it in my free time, and I try to recruit help when and where I can.
I can help.
That slows the process down a bit, So I'm always trying to get funding and some. I do have a technician actually working on that full time right now, so that's speeding it up a lot. But it could be a while before we get to the final stages. And we're going to continue recapturing fish and build that database as well.
Yeah. Data is the important. I can help if you need it, because I'm a developer, but I cannot help with the funding part. Oh, yeah. Oh, yeah, there's somebody here that says that he can't help with the funding part. D'autres questions? I had another question, but I forgot it. Well, it was really condensed information and was really interesting. Thank you a lot. We had a big crowd here tonight, and it was quiet. Everybody was listening to you. I don't know if online we had the reach that we wanted, but it's going to be available for listening further on. So I can thank you enough for spare your time for doing this presentation to us tonight. Thank you very much, Christopher.
Yeah, not a problem. Thank you for having me.
Okay.
Thanks, Brian.
And on that note, we're going to say goodbye to you and thank you very much again.
All right. Enjoy the rest of your meeting. Thank you very much.
Okay, bye-bye.